Hey, Mr. Harrod, I'm here. We're going to go over some atomic fingerprints here and how to fingerprint atoms. Each element has a unique set of wavelengths, which means each element also has a unique set of frequencies. Each wavelength emitted depends on the energy of the electron it releases. The amount of energy that the electron releases depends on the distance the electron moves from the higher energy level to the lower energy level. And remember, each element has a different electron configuration, which means it has a different number of total electrons. This set of wavelengths, when emitted, is called the emission spectrum. It is unique to each element, the emission spectrum. Not any element has the same emission spectrum. Because the emission spectrum is unique, it can be used to identify the element and is sometimes called the atomic fingerprint. Chemical makeup is the distant. This is how we figured out the chemical makeup of the stars, for instance. We figured out the sun was mostly hydrogen and helium, and the ores of samples on Earth can be determined using emission spectra, which I was going to do when I was gold refining, but they didn't set up the machine fast enough for me. Okay, so here's what we have to remember here. In the emission spectrum below, identify which line is. Now, you see this is 410 over here. This is the violet side, okay? Over here, because this is showing me from 400 to 700, 700 is the red side, okay? So which has the longest wavelength? Here, the longest wavelength is closer to red, and it also has the highest number, which will be 656 nanometers. Okay. Which has the highest energy? Well, what you have to remember here is if this is the longest wavelength, right? This means this has a low frequency, which also means it has a low energy. Okay. Compared to the purple side has a short wavelength, which means it has a high frequency, which means it has high energy. So the highest energy here would be 410 nanometers. If you go to the left here, you have to remember there's ultraviolet, X-rays, and gamma that you can't see on this side. On the red side, you're going to see infrared, micro, and then radio. Okay, this just happens to be written backwards because that's what we do. Okay. A sample of unknown element is vaporized and electrons are excited by an electrical current. Good for it. Using the spectra of the known elements, determine the identity of the element. Okay, so basically you have to match the lines here. Magnesium lines, they don't match, so we're not picking magnesium. Strontium lines, oh, those match. Titanium lines don't match. So we're going to pick strontium for this one. Okay. Example 3.6. Emission spectra is a mixture of elements obtained and analyzed. Using the spectra, determine which elements are in the mixture here. So first we look at beryllium. And I see one line that matches, but that's it. That's not good enough. Copper, all three lines match. Oh, I'm guessing there's copper in this. Magnesium, oh, those four lines match. I'm guessing there's magnesium in it. Strontium, I see these three lines, but I don't see them up there, so I'm guessing there's no strontium in it. Titanium, that line, that line, that line, that line, and that line matches. So this is made of copper, magnesium, and titanium. Easily done. Okay, you guys are champions. The legend is out.